Hello and welcome to my video. Here we'll be proving that stereographic projection maps circles from a centered at origin unit sphere down to circles in an xy plane at height z equals -1. I hope you enjoy. Let's imagine that we're in three-dimensional space and we have some vector called n defined by Cartesian coordinates n1, n2, and n3. Let's also assume that n has a magnitude of 1, therefore n1 squared plus n2 squared plus n3 squared equals 1. Let me now draw another vector in R3 called v, which is defined by Cartesian coordinates v1, v2, v3. And let's assume that v is orthogonal to n. By orthogonal, I mean that a right angle can be drawn between the two vectors. Let's now talk about something called the dot product. One of the properties of the dot product states that if you have two vectors that are orthogonal to each other, this means that their dot product must equal 0. In our case, this means that n dot v must equal 0. Since by definition the dot product is also equal to the sum of the products of the two vectors corresponding Cartesian coordinates, we can also say that n1 v1 plus n2 v2 plus n3 v3 equals 0. If you would like to learn more about the dot product, there will be a link in the description to one of 3 Blue 1 Brown's videos covering the topic. So far, I've only been showing one vector that's orthogonal to n, but it turns out that there's an entire plane worth of vectors that are orthogonal to this normal vector, and the same holds true for any arbitrary normal vector in R3. Okay, so we now have a way to define all of the planes that pass through the origin in R3. Hooray! Based on how we've defined our vectors, one of these planes can be written as the set of all vector v elements of R3 such that n1 v1 plus n2 v2 plus n3 v3 equals 0 and the magnitude of n equals 1. I hope you're okay with my set notation. I'm using colons for logical such that's and ampersands for logical ands. The biggest constraint to these planes is that they all pass through the origin. If we want to shift these planes away from the origin, we have to introduce a new value. Let's call this value d, and instead of setting the equation of a plane equal to 0, let's now set it equal to d. Setting things equal to d gives us a way to slide the plane away from the origin by d units in the direction of n. As you can see, with positive values of d, the plane is offset in the same direction as our normal vector. Likewise, with negative values of d, the plane is offset in the opposite direction of our normal vector. I feel the need to mention that the shortest distance from the origin to one of these planes is equal to the absolute value of d over the magnitude of n. Unfortunately, I'm not going to derive this formula in this video, but there will be a link in the description if you want to know where it comes from. Also, don't forget this distance formula because we'll be coming back to it later. Okay, so in our case, since the normal vector's magnitude is 1, this means that our distance is simply the absolute value of d. Okay, so if you fully understand this offset by d, notice that there are timestamps in this video which can be found either in the timeline or at the bottom of the description. I'd recommend skipping this timestamp if you don't need help. However, if you do want to better understand this offset, I want you to imagine that we have two separate definitions for a plane. I'll let plane A equals some arbitrary plane that strictly passes through the origin, defined by vectors v sub a. We know that it passes through the origin because in its equation, we're setting the dot product equal to 0. I'll now let plane B equals some corresponding plane that is offset in the direction of n by d units, defined by vectors v sub b. We know that this is an offset plane because in its equation, we're setting the dot product equal to d. Also, let's assume that both plane A and plane B share the same normal vector n. Now, suppose that we were to take plane A, keep its vectors v sub a fixed in place, along with its normal vector n fixed in place, and then all of a sudden, we set plane A's equation equal to d. Okay, so if this were true, then the equation for plane A would be imbalanced because we just buffed its right-hand side. If you take a look, the name of the set is now question mark instead of plane A because vectors v sub a no longer satisfy the equation. Due to the nature of equations being required to maintain balance, if we buff the right-hand side by d, we must also buff the left-hand side by d. Now, when we add d to the left-hand side, the name of the set then turns into plane B. Let's pull out and dissect this equation for plane B so I can show you why. We can first multiply d on the left-hand side by the magnitude of n. This is the same as multiplying d by 1 because we have a unit normal, so we're allowed to do so. From here, we can distribute out the d's, we can then rearrange some terms. Finally, we can factor out the n1, n2, and n3. Aha! Here, when we increase the right-hand side by d, if the equation were to be balanced, v1a would have to increase by dn1, v2a by dn2, and v3a by dn3. These values inside the parentheses are really just v1b, v2b, and v3b in disguise. In other words, every vector vb is equal to some corresponding vector va plus d times vector n. Alright, so here's d times vector n, and what I'm overall trying to show here is that the vectors of plane B are equal to the corresponding vectors of plane A plus d times vector n. I hope this clears things up as to why positive values of d offset the plane in the same direction as our normal vector by d units, while negative values of d do the opposite. Okay, so we now have a way to define all of the possible planes in R3. Hooray! I now want to add two more conditions to the set for one of these planes. The first one is that -1 is less than d is less than 1. Doing this makes it so that the shortest distance from the origin to the plane must be less than 1. Before I add the second condition, I'm going to add a sphere to the scene whose center is at the origin and whose radius is 1. We can refer to the sphere as the standard 2-sphere, which is just the two-dimensional shell of points at unit distance from the origin in R3. Now, I want you to think about where the plane and sphere intersect each other. It turns out that they intersect along a circle. Just as a side note, if d were equal to 1 or -1, the plane and sphere would only intersect along a single point, but we're not going to let d equal those values in this video. Alright, so there's only one more condition that we need to our set in order to mathematically define the circles that belong to our sphere. This condition is that the magnitude of v must equal 1. Now, the vectors that satisfy all of the conditions are no longer a plane worth of vectors. Instead, it is now a circle worth of vectors that satisfy everything. And as you can see, the name of our set has turned into circle. There's also one more thing that's different. The elements of the set are now that of S2, not R3. Because of this, it's a little redundant to say that vectors v have to have a magnitude of 1 because we're pretty much saying that twice, but I'll just keep the condition there. Okay, let's take a look at these circles. We know that when d equals 0, we have circles whose centers are at the origin, just like how we had the planes which pass through the origin. There is a name for these circles. They're called great circles, and they're the largest circles that belong to our sphere, having a full circumference of 2 pi. We also know that when d is not equal to 0, we have circles that are offset in the direction of our normal vector by d units. I'm now going to add an xy plane at height z equals -1. You can think of this plane as simply the floor that the sphere rests on top of. Let's remove the x, y, and z axes to reduce clutter. I'm also going to rearrange our set right aligned and vertically. We'll come back to the set in a bit, but for now I want to talk about stereographic projection. For those of you who don't know, if we draw a line through the north pole of the sphere and some arbitrary point on the sphere, which I'll call P, this line intersects the plane at some corresponding point, which I'll call Q. The function that maps P to Q for this exact setup can be defined as f of P1, P2, P3 equals 2P1 over 1 minus P3, 2P2 over 1 minus P3, -1. You simply plug in point P, and then the output is point Q. If we had instead defined this line in terms of point Q and the North Pole instead of point P and the North Pole, and then solved for where this line intersects the sphere, we would then be able to derive the inverse of the previous function, which can be defined as g of q1, q2, -1 equals 4q1 over q1 squared plus q2 squared plus 4, 4q2 over q1 squared plus q2 squared plus 4, and q1 squared plus q2 squared minus 4 all over q1 squared plus q2 squared plus 4. For this function, you simply plug in point Q, and then the output is point P. If you want to learn more on how to derive these functions, I highly recommend watching at least one of my previous 2 videos. In one of them, I teach how to derive these functions by parameterizing lines, and in the other video, I positioned the xy plane at height z equals 0 and derived the functions in that case by forming ratios out of similar triangles. Alright, so in order to stereographically project our circles from the sphere to the plane, we're only going to need our inverse stereographic projection function. And let's bring back our set. For this set, instead of circle consisting of vector elements v of S2, I'm going to change it so that it now consists of point elements p of S2. I'm doing this so that it better aligns with our inverse function. And keep in mind that what we want to do is define all of the q elements in the plane. Alright, so now let's plug the coordinates of point P from the inverse function into circle's equation. Doing this gives us all the information we need about the x and y coordinates of points Q in the plane because we're plugging in a special version of P that's defined in terms of Q. Now, because of this, our set of points is defined by Q elements of R3 instead of P elements of S2. Uh-oh, why does it say the name of our set is a tube? Oh, that's because we only have conditions on coordinates q1 and q2, but no condition on q3. So we're actually describing an infinite vertical cylinder with an open top and bottom. Since we want the set to describe a circle, let's set q3 equal to -1. Ah, that's better. This time, we're naming the set circle prime. The apostrophe at the end stands for prime, and circle prime is the image of circle. Vice versa, you can also say that circle is the pre-image of circle prime. The first condition of circle prime is not yet in its simplest form, but the set itself does provide enough information to define the circle in the plane. To help understand where circle prime lands in the plane, if we draw lines through the North Pole and every point of circle, these lines collectively form a cone, and circle prime is just where this cone intersects the plane. The path of projection between the two circles follows along the path of the cone. Alright, let's now get on to simplifying circle prime. We can first multiply both sides of the equation by q1 squared plus q2 squared plus 4. Let's now distribute the terms. I'll then move all of the terms that contain a q to the left-hand side and every other term to the right-hand side. We can then factor out a couple of n3 minus d's on the left and an n3 plus d on the right. Next, we can divide everything by n3 minus d. Hold up, let's stop simplifying for now. We just divided multiple parts of our equation by n3 minus d. Therefore, if we let n3 minus d equal 0, we would encounter division by 0 errors in our equation. In other words, division by 0 occurs when n3 equals d or when d equals n3. Just as a reminder, n3 is the z-coordinate of our normal vector n, and d is how many units away from the origin in the direction of n the center of the circle is. Let's first start off by letting d equal n3. When doing this, n3 remains fixed and circle grows towards the origin. Circle is now forced to contain the North Pole, and circle prime is now just a line in the plane that shoots off to infinity in both directions. Adding d equals n3 as another condition on the set turned the name of the set from circle prime to just line. Alright, let's revert things back to how they were. Now, if we had instead kept d fixed and let n3 equal d, doing so rotates circle upwards, giving us another way to force circle to contain the North Pole, and once again we have a line in the plane, hence the condition n3 equals d. To simplify the first condition of the line in the plane, let's actually take a step backwards and revert back to the equation we had the step right before we performed the divisions. Here, if we let n3 equal d by plugging in a d for every n3, we get this equation. Some of the terms cancel out to 0, then the force cancel out. This equation then reduces to n1q1 plus n2q2 equals 2d. This is the fully reduced equation for our line in the plane. It should look similar to the equation for the planes in R3 that we were defining earlier. This is just the two-dimensional version of that equation. In a serendipitous way, this equation equals 2d. You can also get this equation in y equals mx plus b form if you'd like. This line has its own normal vector, which I'll call n-line, and it's equal to n1, n2. Remember, n1 and n2 are the x and y components of circle's original normal vector. There would then be a line that passes through the origin worth of vectors whose dot product with n-line is 0. Also, since this line's equation is set equal to 2d, the vectors that satisfy the equation for this line are offset away from the origin in the direction of n-line by some distance. This distance, which is actually the shortest distance from this pink line to the origin, is equal to the absolute value of 2d over the magnitude of n-line. Unfortunately, this distance does not reduce to the absolute value of 2d because we can't assume that n-line has unit magnitude. The last step would then be to set the line's z-coordinate equal to -1 for it to reside in the plane. If we are to think of the North Pole as being included in this projection of the circle, we would say that this line contains the point at infinity. This point at infinity is just a single point in the plane that can be approached by traveling outwards in the plane in any direction. If we were to exclude the North Pole, which I'll denote as capital N, the circle then just maps to a regular line in the plane that does not contain the point at infinity. By removing the North Pole, here's what a dynamic projection from the circle to the line would look like. Also, even though it's a line in the plane, especially if this line were to contain the point at infinity, I have no problem still referring to this line in the plane as a circle in the plane, because in topology terms, S1 and R1 union infinity are homeomorphic to each other. Alright, let's go back to this expression for circle prime. To refresh your memory, we ended up here right when we divided by n3 minus d, and I went off on a tangent because we had to watch out for division by zero errors. We're going to simplify this equation even further. First, some of the terms can be rearranged and then some parentheses can be added. Next, we're going to do something called completing the squares. Here, I'll pull out the coefficients 4n1 over n3 minus d and 4n2 over n3 minus d. Next, I'll divide these coefficients by 2. I'll then square them. Let's now distribute out the squares. Now, let's throw them back into our equation. Okay, since we just added the left-hand side by these two values, we must also add them to the right-hand side to maintain balance. Okay, from here, let's first tackle the left-hand side of the equation, which is really just now two second-degree polynomials being added together. For the first polynomial, I want you to ask yourself the question, which two terms can be added together to equal 4n1 over n3 minus d, and multiplied together to equal 4n1 squared all over n3 minus d squared? Well, the answers to that question turn out to be 2n1 over n3 minus d. Likewise, for the second polynomial, following the same logic, we get answers of 2n2 over n3 minus d. Based on our answers, I'll rewrite the two polynomials out the long way. Terms can then be combined, which finally brings us to the fully reduced left-hand side of the equation. Now, looking at the right-hand side, as you can see, it consists of three terms being added together. So we can first start off by forming a common denominator in the first term. We can then combine the three terms now that they share a common denominator. I'll then distribute out the numerator. Then after factoring out the 4 and rearranging some terms, we now have a fully reduced and hopefully more recognizable equation for circle prime. Hooray! Let's throw it back into the set. For those of you who need a refresher, the general equation of a circle in 2D space is x minus x naught squared plus y minus y naught squared equals r squared. And this is where x naught y naught represents the center of the circle and r is the radius of the circle. If you take a look at the first condition for circle prime, it matches the general equation of a circle in 2D space. The only catch to circle prime is that it's embedded in R3, so we have to make sure that all of its points have a last coordinate of -1. Alright, so this means that the center of circle prime is minus 2n1 over n3 minus d, minus 2n2 over n3 minus d, -1. And we can pull out the negative from all of these coordinates. This term on the right-hand side is the radius squared. The radius is then the square root of this term, and I'll go ahead and pull out the 2. Okay, we're getting close to done, but we still haven't proven that circle prime is indeed a circle. To do so, our final steps will be to prove that the center and radius of circle prime are real. Okay, so we're going to initially assume that n1, n2, n3, and d are all elements of the real numbers. I'm also going to mention that real numbers are closed under addition and multiplication. If you take any two real numbers and add them together, the result is some other real number. The same holds true for multiplication. Since subtraction is the same as adding a negative real number, and since division is inverse multiplication, real numbers are also closed under subtraction and division. Based on all of this, and the fact that integers are also real numbers, we can imply that all of the coordinates of center, which I'll refer to as center 1, center 2, and center 3, are all elements of the real numbers. Therefore, center is an element of R3. Okay, now I want to remind you of these two conditions we have on circle prime. The first being that we have a unit normal, and the second being that d is between 1 and -1. From these two conditions, we know that n1 squared plus n2 squared plus n3 squared must be greater than d squared. We can then bring d squared to the other side. Now, if you take a look at this inequality and then take a look at the radius of circle prime, it should be easy to see that the numerator of the term inside the square root will always be positive. Likewise, otherwise the denominator of the term will also always be positive because it's being squared. Therefore, the radius of circle prime is a real number because it equals the square root of a positive real number. If it were a square root of a negative number, then the radius would be a complex number, which isn't good. Alright, getting the equation of circle prime reduced down to its final form, and showing that its center and radius are both real elements, proves that circle prime is indeed a circle. That about wraps it up for everything I had to say for this video. Liking, subscribing, and commenting will all be greatly appreciated. I hope you enjoyed the outro.